it is two functions, two functions, one is on the atom A and atom B, and both the hydrogen dimers are, both the hydrogen molecules are described by the minimal basis. So once you have minimal basis, you have, am I audible?
Yes, sir.
Yeah. So you have two molecular orbitals, because as you know from Hartree-Fock, if you do two atomic orbitals, then you get two molecular orbitals. So for each of the hydrogen molecules, these hydrogen molecules are interacting. There is no dissociation of the hydrogen molecule by itself. Dissociation is between the two H2. So I hope the problem is clear. So it's a H4 which I'm dissociating into H2 plus H2. So I have sigma I will have excitation, apart from the Hartree-Fock of the H4, I will have one pair of excitation between sigma G and sigma U on the atom A, another excitation between sigma G and sigma U on the atom B. There will be no excitation between A and B because they are infinitely separated. So with that, Hartree-Fock becomes this, and then there are two terms in which sigma G is replaced by sigma UA here, and sigma GB is replaced by sigma UB here. So compared to Hartree-Fock, each of these is doubly excited configurations. So these are the only two doubly excited configurations. So I have my psi di, which contains three configurations. So that is what I first stated. Then I said, when you calculate the integral that will appear are Hartree-Fock and one of the doubly excited configuration. So we define that as the K12. And another type which will come is between a doubly excited to a doubly excited. And there we said that if it is a diagonal, then it will be K12. That one, the same doubly excited on both sides. That is what I mean by diagonal. And if it is off diagonal, that is one doubly excited here with another doubly excited, that will be actually four excitations. So four spin orbitals differences, so that will become 0. So with that, we actually set up the matrix element, and you can see that when I know these are K12 by symmetry, this will be also K12, and here 2 delta, which is the diagonal term, right? So then we solve this CI equation. So this will be this matrix element into the coefficient, E correlation into the coefficient. And remember, now when I set up the CI matrix, it is not the H, but the normal order H, which is Hn, or H minus E Hartree-Fock. Okay. So obviously there will be difference here that this will actually become 0. And these two are 0 for Slater group because there are 4 occupancy differences. So I hope the matrices are clear. Also, because we are using intermediate normalization, so this is 1, and then C1, C2. So that is how I set up the equations. And I think by trivial example, we saw that these, you get C1 equal to C2, and this is what you get in doubly E correlation after you put it back, and you get a quadratic equation, and then you get a root, which is this, the lowest root. Okay. I had also given that the same exercise you do for the monomer and find out that the monomer correlation energy is just this. Okay, so there only will require the same type of terms, right? So dimer DCI is this, monomer DCI is this, and if you do similarly nmer, it will become n here, square root n here, and this would mean that the correlation energy goes actually proportional to n rather than proportional to square root n rather than n. Okay, when n is large, this is going to be the dominating term. Is it clear? Of course, you can do a binomial expansion and see all that, but this is going to be for large n. So this is actually for large n. Okay, so n is large. If n is small, you cannot make such meaning. So it also means that because the monomer energy and the dimer energies are related in the manner which is square root 2 rather than the 2 times this, it also means that the DCI is not a good approximation because it cannot dissociate correctly. Is that all right? with this today, I will move to now DQCI. So which is doubles and quadrupole CI, and to see what results we get from the doubles and the quadrupole CI. Okay, I just wanted to know that particular assignment should be submitted by this Friday. Okay, please remember. Next Friday, by 26th, you should submit the assignment. So when I do the DQCI for the same problem, I have now doubles and quadruples. So for the quadruples, you will have an extra term, which will be basically the four-body excitations, and that will happen by the two pair excitations taking place on the A and B simultaneously. So essentially, that is the meaning of quadrupole excitations, that the results that you will get now has extra configuration. So the other thing to remember is that when we do this, the H4 problem, the DQCI becomes exact. Okay. So if you write, because it's a four-body excitation, so there cannot be any four-electron problem, so there cannot be anything more than DQCI. Is it clear? I don't have singles and triples because what is the reason? Because I am looking at the capital sigma state. So you should be able to set up the equation now. You should be able to set up the equation now. So first of all, write down what is the DQCI wave function. So this will also become sigma g a square, sigma g b square. Again, I'm writing in the intermediate normalization, plus a coefficient sigma g a is replaced by sigma u. The b remains in sigma g, plus C2, where A remains in place, and there is an excitation in the B. So this is your DCI, and then you have an additional term now, which is a quadrupole excitation, which means both, if all the four electrons are excited, so this will become sigma u a square, sigma u b square. Is it clear? Hello?
Yes, sir.
So you'll have four terms. Of this. So the entire CI problem now simply becomes 4x4 problem. It's not really very difficult. We did a 3x3, now it becomes 4x4. But the important thing is here to set up the CI matrix, and then you should be able to do it. So what are the CI matrices? Please let me know how will you define. So what are the new terms that I will require? Please remember that I already have matrix element, which is between these, of course, is very easy. That's the Hartree-Fock, and that is 0 basically. Then I have matrix element between doubles and Hartree-Fock. So let me write down that CI equation that I was writing. So I'm just writing down the H matrix now. So the first term is 0. The second term remains K12, which is basically the Hartree-Fock with one doubles. Hartree-Fock with another doubles also remain K12. What happens to Hartree-Fock and this quadrupole term? Can somebody tell me?
0. Differ by 4 orbitals.
Great. Because 4 electron. Here it is 0 for a different reason, because I am subtracting E Hartree-Fock. The subtraction of E Hartree-Fock has no meaning here, because the Hartree-Fock separates and they are any orthogonal to each other. So it is only the Hamiltonian matrix element. All right. Now I go to the next row, which is, let's say, double excitation. So let's say K12 with the Hartree-Fock. And now I have a doubles to doubles, which is 2 delta. doubles to this doubles is again 0. Now the important terms that are coming for the first time, 1 doubles with quadruples. Can you tell me what? Just look at this. Will this be 0? See, this doubles to doubles is 0. But will this doubles to quadruples be 0?
No, differ by 2 orbitals.
That's very interesting. Because many people might think doubles to doubles should not be 0. But here doubles to doubles is 0. We have the 2 off-diagonal doubles. But quadruple it is not 0 because at least one of these configurations will remain the same. So this will actually mirror Hartree-Fock doubles. Is it clear? So if you look at the Hartree-Fock doubles, it is exactly this. You have only one that is different. So this will also become K12. Is it clear or not? Please let me know for those whom it is still not clear. Then I can trivially do the next one, which is again exactly like this. So K12, but now 0 will come here, 2 delta will go here. That's the only difference. The diagonal term will survive. The diagonal term will survive with 2 delta. This will again become K12. Is it clear? The second and third row. Then I go to the fourth row, where again this is quadruples with Hartree-Fock first. That is 0, because this is 0. Actually, trivially you can write down the fourth row. These 3 terms, because they will be symmetric. So I have a K12, K12. What will happen to this term? If the diagonal of the doubles is 2 delta, it is very easy to show that the diagonals of the quadruples to quadruples will actually be 4 times delta. So the same integral will occur twice. Okay, so let's define that as 4 delta. The diagonal term will be quite different. Okay, but let's call it 4 delta. And now you have 1, C1, C2, C3. It suffices to understand that these diagonals are not same. That is very important. As the dimer E correlation, and now it's really like full CI. Okay, 1, C1, C2, C3. So this becomes your CI equation. And I think you should be able to solve it. So first thing is C1 to C2. You write down the second and third, you will see they are identical. So it's very easy to show that C1 is equal to C2. And if C1 is equal to C2, then of course, you can go back to the first equation, which says E correlation equal to K1 to C1 plus K1 to C2, which would mean that E correlation would now become 2 times K1 to C1. This is exactly the same that we got in the DCI problem. Because if you see the first row into first column, it's K12 into C1 plus K12 into C2. This is anyway 0. So E correlation. So these 2 equations come out very easily. I think you can just set it up. I did set it up, but you can set it up. I will not give as a home assignment problem, but you do as a practice problem. Anything from here may come in exam. So I'm not giving as an assignment problem. But I hope you'll be able to set it up. It's very trivial to see. Then the next equation is to get C3. So how will you write down this C3? And you should be set it up. I'll just write down the final expression. E correlation divided by, it's very easy again, minus 4 delta. So that will become C3. And you can see this. It's very easy to do. This into C3 equal to 0, K1 to C1, K1 to C2 plus 4 delta C3. And you have K1 to C1 as twice as E correlation. So you can write down E correlation twice and quickly get to this expression. Okay, so that twice it will come. So this is for the dimer. Okay, this is not 2. This is superscript 2. Okay, and hence you can show now that C1 is equal to 2K12 2 E correlation minus 4 delta. So this is the only difference from the dimer. If you remember in dimer it was 2 delta. This will now become 4 delta because this has come here. So you please look at these two expression and get the expression of C1 from here, and you will get this as 2K12 by 2 E correlation minus 4 delta. Please derive this at home. And finally, once you get C1, go back here, substitute this, and you will get the dimer E correlation as 2 times delta minus delta square plus K12 square to the power half. Which is exactly twice the monomer energy. I have written down all the equations. I think this is quite trivial, but please do this exercise. I'm not giving you as a home assignment problem, but I'm giving you a fairly good idea that any mixture of these might come in the actual exam. So please do at home peacefully. I've written down all the equations. It's a very simple algebra, a 4x4 algebra, which I'm doing iteratively, basically. All right. What is interesting is to see the C3 equation. Let me go back to this equation of B. Dimer E correlation divided by, I wrote it down, dimer E correlation minus 4 delta. So this is the expression. Once you are able to derive, then you can write this. Now what I do, I substitute in the dimer E correlation this value. 2 times K1 to C1. 2 times K1 to C1. So what I will get here is, this is not 2, I'm again repeating. This is a dimer E correlation, just the 2 is in this superscript. So this becomes 2 times K1 to C1, okay, divided by dimer E correlation minus 4 delta. Note what is C1. Now apply C, equation C. C1 is precisely this. I hope you are able to see this. So this equation is very, very important. This equation is also different from the value of C1 in the dimer. That was 2 delta. Here it is 4 delta. Of course, C1 is still equal to C2, but the values are different. But what is more important is C3 is now equal to C1 square. Is it clear? Please do not worry about actual derivation of the algebra that you do at home. But what I'm now trying to show you is a very important physics, that the amplitude of the 4-body excitation is nothing but square of the 2-body excitation in a full CI. This is now full CI for H4. So I have H4 system. Let me write the schematically. Sigma GA, sigma GB, they are well separated. And you have sigma UA, you have sigma UB. So I have this as the Hartree fork, and now I'm saying that there is an excitation amplitude of this to this. So this is independently C1, where C1 is equal to C2. But when I'm exciting both simultaneously, that is C3, they are nothing but the product of the individual double excitation. Product of individual double excitation. And this is exact. In this dissociation limit.
2 times K1 to C1 minus 4 delta.
And that is exact. In this dissociation limit. 2 times K1 to C1 minus 4 delta. 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 2 times K1 to C1 So in the dissociation limit, this quadruple excited configuration that I wrote, C3, is actually nothing but C1 into C2 or C1 square. So everything can be written in one parameter, C square, right? For this four-body problem. And that's a very interesting realization. And that I told you that the four-body excitation does not necessarily take place with all four going together, because the chances of all four coming together is very small because of the Pauli principle and the two-particle nature of the Hamiltonian. So in the case of the dissociation limit, they are exactly product. That means they're independently taking place, and total probability, see, remember, these are all probabilities. So total probability will be the probability, the square of these are the probabilities. So the probability of this into this. And that is exactly what you get. So if the amplitudes are squared, the probabilities will also be squared. And that is a very important part to understand. But what is more interesting is that even when they start interacting, so in the interacting limit, also I can say the C of the quadruples will be roughly the product of the C doubles. I will just write this. What kind of product I will not qualify, even in the interacting limit. This is, of course, a dissociation limit where it is exact, because this is coming from the equation. This is exact analytical solution that I'm giving, okay, of the DQCI. So this is exact, but then there is an approximation which says that even in the interacting limit, the quadruples is best written by product. But if I write this, then this does not have a CI structure, because in CI, everything should be linear variation, right? This term is no longer linear if I write this, but this is the dominant approximation. Actually, it is somewhat different. So you have to write for full CI quadruple separately. Only in the dissociation limit, I repeat, it is exactly product. But otherwise, it is not exactly product. But if you write this approximation, then it is no longer linear, because this comes as a nonlinear term, C square. And this is precisely the content of the couple cluster theory. Which is basically nonlinear. So since we have sufficient time, I'm sure the couple cluster will be addressed, at least to some extent, in this course. Not to a great length, but it will be addressed. So couple cluster is a nonlinear wave function. It's not a linear wave function. If you do variation, linear variation will not apply. Okay? So that's a very interesting thing that I wanted to tell you. And you can now see, most importantly, that the correlation energy is twice the monomer energy. So the dissociation limit results are properly obtained. Please let me know if there is any confusion from this part.
Sir?
Yes.
In dissociation limit, the C3 becomes, the quadruple coefficient becomes square
Product.
or double square of
Right.
that is. So, but we are doing full CI.
Yes, full CI only.
But the coefficient has become non-linear now here in this case. So
it is
a special case.
This is a special case. So both are identical. So because it's full CI, if I do couple cluster for this, and because in couple cluster also there is nothing more than T2 square, a square of the product. So they are identical for dissociation. Correct. That is correct. So if I do, as I said, when I set it up, I did not assume. I assumed a linear variation, right?
Yes.
If you look at my wave function, I did not assume anything. After I do the solution, it turns out that it is like C1 square. So that is something I cannot help, right? I did not assume that they are product to begin with. Okay?
And in couple cluster, we assume that
we assume this from the beginning.
Okay.
So couple cluster has that will be an approximation for the interacting limit. But of course, that's an approximate couple cluster. I can have a full couple cluster also, but then there is no point doing full couple cluster. But the approximate couple cluster doubles will also take care of the quadruples. in an approximate. That is the beauty of coupled cluster. So I will do coupled cluster doubles, but normally when you say double, there should not be any quadruples, right? But coupled cluster doubles will take care of the product of the doubles, and hence quadruples will come in, and that's the beauty, and that will essentially take care of the dissociation problem of DCI. You saw that DCI did not have a dissociation problem, only I had to do full CI. But coupled cluster doubles, when I do, even though it's an approximate, within this approximation, it will at least have size consistency or dissociation problem. So in summary, DCI has a dissociation limit problem. And of course, full CI is exact, so there is no problem. Anyway, full CI is no problem. And that is what we showed, that DCI could not break, but the full CI or DQCI could. In this particular case, DQCI is a full CI. Okay. But of course, if I had taken H6, H2, I had to do the DQ extra CI. Otherwise, this would have been still not right. Quadruple would not have given me right, because there are another configuration would have been missed out. Okay, you understand? But coupled cluster takes care of all such products. So obviously, I don't want to discuss coupled cluster now, but that is the beauty, that this is what is called the size consistency problem. So essentially, size consistency means that energy of AB should become energy of A plus B in the limit where RAB goes to infinity. So that is what it should be. So any theory which does not satisfy this is not size consistent. So CI, exact CI is of course size consistent, but the approximate CIs are not size consistent, but we will later see that even approximate coupled cluster is size consistent. Okay, is it all right? Okay, so now what I am going to do is to write down the same DCI problem a little bit more generally. So psi DCI, a little bit more generally, because I wrote it in minimal basis for only dissociation problem, but now I'm going to write a more general problem. So phi Hartree-Fock plus the double excitation, which I'm writing as A less than B, P less than Q, C, AB, PQ, phi AB. I hope you understand the difference from what I was doing. In the earlier case, there are only 4 electrons, 2 orbitals. But now it is more general. A, B are occupied, so it's an n electron problem, first of all. And there are many virtual orbitals. So I'm writing a more general form. Is it clear? And then I write down the CI equation, just like I did for the projection method. Let me do the CI equation by projecting. So what would be the CI equation now? H minus E Hartree-Fock. This, let me write it fully, psi DCI, phi Hartree-Fock, plus sum over A less than B, P less than Q, C, AB, PQ, phi AB, PQ, the 2 electron excited determinant, equal to E correlation phi Hartree-Fock plus okay. So I just wrote down the thing, and then I told you that whatever I did the matrix eigenvalue equation, I can also derive by projection, and that is what I will do. So let me project first phi Hartree-Fock, and you will know the equation already. Phi Hartree-Fock, H minus E Hartree-Fock, phi Hartree-Fock is 0, so that will become 0. So only this term will survive on this side. So we have phi Hartree-Fock, phi ABPQ. Sorry, let me write it again. Phi Hartree-Fock, H minus E Hartree-Fock, with H minus E Hartree-Fock is acting on the full wave function. H minus E Hartree-Fock, phi ABPQ, C ABPQ, sum over all of them. Remember, for a dimer problem, there was only one integral, and that was called K12, if you remember. This is exactly what was called K12. Okay. Equal to, come on this side, E correlation, phi Hartree-Fock is 1. Phi Hartree-Fock is orthogonal to double excitation, so you just have E correlation. And this is exactly what we got. If you now can look at the dimer or the tetramer problem, this is exactly what we got. E Hartree-Fock is incidental here because this comes out and they are again orthogonal. So what is important is just the Hamiltonian matrix element, and this is what I call K12. So let me write the E correlation as the only term, A less than B, P less than Q, phi Hartree-Fock, H, phi ABPQ, this integral into C ABP. If you remember your DCI correlation energy for dimer or whatever, monomer, it was the K12 times C. Okay, and there are two double excitations, so it was times 2 K12 times C. Right? If you remember, there is one more double excitation. Here, I'm just writing only one term. So this itself had two terms. A less than B, P less than Q was in center A and center B. So this comes with twice. But one of them was K12. I hope you can correlate this very easily, what we did. Then the next is the equation for C, where I project this equation with a member of the double excited configuration. So let me write this configuration as, let's say, phi CDRS. So another double excitation. Of course, this is the ABPQs are used as dummy, so I'm using some other CDRS. So now again write down the H minus E Hartree-Fock. So I basically the same Schrodinger equation I'm now projecting with one of the double excitations. So phi Hartree-Fock, okay, and then doubles with the doubles, so it will become sum over A less than B, P less than Q, phi CDRS, H minus E Hartree-Fock, phi ABPQ, C ABPQ, right? Equal to, when I do on the left hand side, you can immediately imagine that because of orthogonality, only terms ABPQ that will survive is that which matches with this CDRS. So it will become E correlation times C CDRS. I hope all of you can see that. That's basically the CI equation. So when I do with the phi CDRS, E correlation will anyway be there. This will become 0. And this is orthogonal to each other. All terms, there's a delta condition. Only when AB is equal to CD, PQ is equal to RS, it will survive with that as the coefficient. So I have these two sets of equations. I hope it's clear to all of you. And this is what exactly I wrote for the dimer. I'm now generalizing this equation. Is it clear? Then what I'm doing is to write these two sets of equations in a matrix form. Remember, the E Hartree-Fock is incidental here because that will actually is a number, so the rest will become orthogonal, so I can remove E Hartree-Fock. Okay, it's not important. So let me define some matrices. Phi CDRS, H, phi Hartree-Fock. So this will become like a column matrix B with elements as CDRS. That's the element. Or CRDS. You can say CRD. So that I can make it square matrix, a column which is this number, CRDS. So the number of elements which are number of doubly excited in the column. Okay. So remember, this was nothing but K12. That time it was a number. Okay. Or two numbers at the most for dimer. Then I have this very important diagonal, doubles with doubles. So let me call this phi CDRS, H minus E Hartree-Fock, phi ABPQ. This I am calling the D matrix. Then this was precisely my 2 delta there. 2 delta, 4 delta, whatever. So this is nothing but D Again, you can say that CRDS comma APBQ, whatever you want to write. It's a square matrix, as you can see. Number here and number here is identical. It's a square matrix. Remember, here you cannot remove E hat of A priori, because if these CDRS and ABPQ are identical, then they are diagonal. So some of the diagonal elements E hat will be subtracted. I hope that is clear. Somewhere else it will be there. So this actually stays. With this, and the C is itself is a column matrix, I can write the equation very easily. So if you see this equation, this is a column matrix. This is the adjoint of the B matrix, the way I have defined. I have defined B matrix with this as a doubles here, but now the doubles is coming here. And since this is ABPQ, I can say that the E correlation is nothing but B dagger C. So note that C is a column matrix, B dagger will become a row matrix, so it will be number. So everything, all matrix multiplications have been survived. Then the second equation, which is just this is again B. I've already said this is B, no problem. This is my D, this is again my C. And here is E correlation C. So you can write this equation as B column plus D is a square matrix times a column C equal to E correlation C. I hope you can see this very easily. So your E correlation is nothing but column B dagger, so that becomes a row times the column C, and the column B plus the diagonal matrix D, not diagonal, sorry, the square matrix D times the column matrix C is E correlation C. So this is a very simple way of writing this DCI equation in a matrix form. You can actually generalize very easily, and this is exactly what we did for the dimer, because if I write it H2 dimer or H2 monomer, whatever you do, if you write it in a simple equation, it becomes 0, B dagger, B, D, 1, C equal to E correlation 1C. So that's your DCI. So when you set up a monomer equation for the assignment, it's very easy. These are your K1, 2. Then you have 2 delta, and you can very easily set up. And you can see that this satisfies these two equations. First equation gives you this. Second equation gives you this. Okay? I hope all of you can do the multiplication. It's just matrix multiplication. And you can set up this equation very, very easily. And then that is what I exactly do. I solve this equation iteratively. So I can diagonalize this matrix, or the same diagonalization can be shown as an iterative procedure, and this is called iterative diagonalization. So diagonalization procedure, iterative procedure for diagonalization. So I'm solving the diagonalization by means of iterative procedure by expanding this here. So what do I do now? I write from this equation, I write an expression for C. So just see this expression. Column C is minus the square matrix D minus this identity square matrix times E correlation. So this means E correlation is actually subtracted from the diagonal, right? Inverse B. I hope all of you can derive this very easily. So what you do, D minus E correlation C equal to minus B. So C will be minus B, minus D minus E correlation inverse B. Remember not to swap. Keep it like this. So this is also a square matrix times a column gives you a column. Always you should see that the dimensions are matching. So this is what you get. C, substitute back here, you get E correlation. So E correlation will then become minus B dagger, and then you put this D minus identity E correlation inverse B. So this becomes an iterative equation for E correlation. Why is it iterative? Because I don't know E correlation. I have to keep iterating. Finally, I get E correlation, which will be also my eigenvalue equation. So a very important message is that an eigenvalue equation can be solved iteratively. So I have an iterative equation for the
Sir,
eigenvalue. Yes. And of course,
sir,
I'm going
can
to
you
get
repeat?
one of the eigenvalues. Yeah. No. So
Yes,
this,
can you?
yeah. So this is my eigenvalue equation, right? So there are lots of procedure to solve the eigenvalues of a matrix. Jacobi, Householder. I am not using them. I am writing these equations in these two forms. So remember that this and this is identical, correct? Because if I multiply the two matrices, I get this. And that is what I did from here. This is my CI equation that I set up, which is same as the eigenvalue equation. Now, instead of solving the eigenvalues, I prefer to solve this equation in an iterative manner. So first, I'm getting C from this equation, then putting C back here. Correct? So that's a very simple substitution. C column I'm substituting, and here, and then I see that E correlation comes out, but it is an iterative procedure because E correlation on the right is also there. Why did it happen? Because here itself there is E correlation. So when I separating C out, there's a D minus E correlation inverse. So that is what has gone here. Is it clear? It's a very simple algebra. What's so difficult to understand? So I'm basically substituting from C. First note that this is the equation that I got by projection, method of projection. That's my linear variation, basically. Which is linear variation because these same two equations can be written in this manner. So you can say that the linear variation, I get matrix eigenvalue equation. So these are the matrix eigenvalue equations. So all of CI is always matrix eigenvalue equation. I could have straight away written this. Instead, I showed by method of projection. Is it clear? Because I told you that in a linear variation, method of projection is also a valid means of getting a variational equation. If you directly vary the linear variation, you will anyway get matrix eigenvalue equation. Okay? But by projection, you can get the same equation. So I first did a projection method, and I got this equation by defining the column B, column C, and a square matrix D. And then I showed you that indeed it is an eigenvalue equation. But then I said, instead of solving the eigenvalues of this matrix, I prefer to solve it in an iterative manner. So I wrote C here, substituted here, I got E correlation in terms of E correlation. And now I can solve it in an iterative manner, but if I first assuming that the E correlation is 0, so I'll get a value of E correlation. That same E correlation goes here. Keep doing till the values converge. So this is my guess, initial guess. All of you know what is iterative procedure in mathematics, right? So iteratively, I can converge at least the ground E correlation value. This works well for the ground state because when I said E correlation equal to 0, it is actually a Hartree-Fock approximation, right? Because in Hartree-Fock, E correlation is 0. So in a way, I'm starting from Hartree-Fock approximation and then building the correlation energy. So this is another way of looking at the CI problem. And clearly, in the very first guess, if E correlation is 0, what will be the first guess? So I can write E correlation in the first approximation would be equal to minus B dagger. This will become 0, D inverse B. But D is that matrix. Don't forget what is D. D is this matrix. H minus E Hartree-Fock between doubles and doubles. So that is a square matrix, of course, because doubles on this side, doubles on this side. So invert that matrix, do a column B on the right, a row B on the left. Multiply and take a negative sign. Negative sign is very important, huh? Don't forget. And that is why the correlation energy always will be negative. So if this is the Hartree-Fock, when you add correlation energy, total energy will go down. Energy always goes down. But if this is exact E naught, then it will always remain above exact E naught. So this may be your DCI, for example. But it is going down because correlation energy is negative. Because the way I have defined correlation energy, it is negative. Okay? So my correlation energy here is basically E naught minus E Hartree-Fock. So that's always negative. Yeah, please ask question if there is any confusion here. So this is the first approximation. Of course, you don't stop here. Then you put this back here. Next approximation, you continue. It becomes more and more messy. More number of B dagger B comes. But at the first approximation, it is very simple. So if you just make this guess, at least you get some correlation energy. And later on, you will realize that this is very close to what is called the second order perturbation energy. We'll show this later, that when you do MP2 perturbation theory, MP2 is a second order energy, which will be very, very closely related to this, not exactly. So one can define from here in MP2. And that therein will lie a connection between perturbation theory and variation theory. Because this is done by completely different procedure. Okay, I will stop here. And I will ask any questions if you have.
So that correlation one means it is first order.
First, no, not first order. It is first approximation, first iteration.
Okay.
I'm iterating, no?
Hmm.
That it will be related to a second order perturbation theory is a different matter. We have not done this. We'll see this later.
You are expanding the D minus E correlation inverse.
I am not expanding. I'm not expanding. No, I'm doing iterative manner, which means first guess was E correlation is 0. I put this here. I take a B dagger D inverse B. Then, so in a way it is expansion. You can say that. But I'm not generating by expansion. Then the next time what I will do, my E correlation 2, I will tell you what will happen. This is E correlation 1. My E correlation in the second iteration, this is iteration again, will be minus B dagger D. Now I will add this E correlation 1. So minus D multiplied by a square matrix identity into E correlation, which is nothing but minus B dagger D inverse B. This is a number, right? And the whole thing inverse B. So what I've done, I'm actually going back to my master equation, except that here I'm substituting the first iteration value. Correct? And keep doing. This will be my E correlation second iteration. Next time, here I will put the second iteration value. I'll get third iteration. Do you understand? In a way, this is like expansion. You are right. If I do inverse expansion, also I will get a power series in E correlation. I'm in a way generating that, though terms of the power series in a different way. So these kind of solutions are called iterative solutions to the diagonalization of a CI matrix. Now, depending on how do you iterate, you have different types of procedure. One of the most famous procedure that is known today is called the Davidson's algorithm. It is very well known. It is there in many, many textbooks. So the advantage and the disadvantage. The advantage is that if I would have diagonalized a big matrix, this is of course a small matrix, DCI, but this D can be very large. Remember, this is a block. Actually, this is not a 2 by 2 matrix. It's a block 2. Because depending on the number, D itself is a big square matrix, right? So I have just written as a block. This is also a block of row, like for H4. It was 4 by 4, correct? So even in minimal basis. So in a larger basis, this is not a 2 by 2 matrix, but this is a 2 block by 2 block matrix. Is it clear? Because each of these B and D is a block, correct? So in a way, if I solve this equation by actual diagonalization, I will get all the roots. So diagonalization gets me all the roots, but it is expensive. If you do a full diagonalization, you get all roots, but very, very expensive. Whereas an iterative diagonalization, depending on the guess and my guess is good that I'm getting the ground state, I can get a few roots, a few selected roots. And it's a faster procedure. Very often in quantum chemistry, we don't need these all roots. What do I do with all roots? Most of the time, I'm interested in ground state and maybe for few excited states, few other states. So the iterative diagonalization comes out very well. And the diagonalization procedure that I said with E correlation equal to 0 gives you ground state nicely. So this gives you a very nice recipe to converge to the ground state equivalence, the lowest state. Okay, so please read this part. I've done enough today. The H4 problem plus the DCI problem I already wrote, and now I wrote more generally, and I solved it analytically that time because that was very easy. But here numbers are large, so I'm showing you how to make an iterative solution. In fact, this iterative solution you can try for my H4 problem with minimal basis. You can try. I gave you analytical solution there because it was easy to solve, but you can try, you will immediately converge to the final solution. You understand? So I think it's very interesting to play around. The most important thing that can be covered next time is that for a linear variation has much more of an interesting because of a theorem called the Euler's Mcdonald theorem. Sometimes it is called Mcdonald separation theorem, the Hume. And this will actually tell you that the CI has not only bounds for the ground state, but has also bounds to the excited states. And that is why the CI is very nicely used for excited states. And I told you, if you even do just CIS, then you can get excited states. Not good, but you can get. Of course, CIS doesn't give you ground state because of Brillouin's theorem, I told you before, but you can get excited state. But more importantly, any CI, any linear variation, the roots that you will get are also bounded from the top by the excited states, the corresponding roots. So it is not only a ground state upper bound theorem, but also for excited state. If you remember the Rayleigh-Ritz variation principle, it only said greater than or equal to E naught. But now you will have excited state upper bound, which will be actually captured in the Mcdonald theorem for the linear variation, which we will like to cover in the next class, which will be on Monday. I will not be able to cover on Monday. I am going out, but madam, I will request madam to cover this linear variation. After you understand linear variation, I think with a little bit of example, CI problem can be closed. And then we will take up the perturbation theory. Okay, are there any questions today? Please go through this properly. They're just very trivial algebra, as you can see. You will have the recording. You can see the recording. I will upload the slides, I think. But these are straight away taken from Zabu and Oslur, with some indices may be changed. Like they call this psi, exact phi, they call this CDTU. I think all that you should be able to handle. With the symbols changed, it is pretty much, the basic idea is pretty much the same, but I have done nothing new. I have set up the CI equation by method of projection. Then I have tried to set up this as a matrix equation by defining these columns and square matrices, and then showed you an iterative procedure. Before that, I had already done very similar types for H2 dimer, DCI. Today I showed that DQCI gives you exact result. So the dimer energy is twice the monomer energy. The evaluation of just the monomer energy was your assignment. DQCI also, I did not derive everything, but as I told you, some of these, so this is basically the same equation that I was doing in a full form, not the block. So I told you that you should do these things before. So why it was block? For example, this part that I wrote was my B dagger. I don't identify. This was my B. If you go back, you'll see very quickly. This is my D. This square matrix is my D. and this is my C. It's a 4x4 problem. So out of which one of them is Hartree-Fock. So I forget about that. So I hope you can see this. 0, Bidagar, B, D. 1, C. E correlation 1, C. Please see this. 0, Bidagar, B, D, 1, C, E correlation 1, C. Now I hope you get it. So these are the blocks of all doubles, doubles into doubles, Hartree-Fock with doubles, and so on, and conjugate. Coefficients of all doubles. Hartree-Fock is anyway there, 1. So actual number you have to add 1. The Hartree-Fock you should not forget. But this block is 1 less. Okay, so I just wanted to identify that this is exactly what we did. We didn't call it block, but this is what is your D, this is a Bidagar, this is a B, this is your C. So your blocks are all 3 dimensional here. Hartree-Fock is 1, so total you have 4 determinants, including Hartree-Fock. All right, is there any more questions? All right, so I will then stop here.